So as Vikas said, I'm going to take a little bit more deeper dive into some of our system architecture, what we have in our Violin systems here. Pardon me. So as we touched upon, we have a very modular design, and this gives us a few benefits. It's the key to our resiliency in that pretty much everything we see here there's at least two of. There's 2 array control modules, 2 memory gateways, the VCMs, up to 64 VIMs. We have multiple HBAs and NICs, power control modules, power supplies, et cetera, et cetera. The entire system is built from the ground up with redundancy in mind. But this modular design also gives us the benefits, as Vikas and Steve alluded to, is that it's pretty much piecewise upgradable. New VIMs come out, or new flash comes out, we move to a higher density VIM. The VIMs can be changed for a new product without having to redesign the entire architecture of the entire system. As we ride the Intel train with the memory gateways, we moving from Ivy Bridge into Broadwell and beyond. The memory gateways increase, and we take into account the new memory that's available and the density, and it all thrives without having to be a completely new chassis redesign or new interconnect redesigns. And the other thing that this gets us, and we'll talk about in a little bit, is basically a parallel design leading to better performance.
So do you guys support like a memory cache in your controller, or is it all on SSD? Or?
We'll get a little bit into the data path, but at various points in the path, there are some points where DRAM is used for some degree of caching, but at all points, it's basically in a protected mode. We have a lot of DRAM down at the VIM level, which actually is
something like that.
So it's an excellent question, and you picked it up rightly. So since we own our VIM, as you will see, there is a DRAM on there. We leverage that, as well as the system DRAM that we have in the controller module as well. Very good thing that you picked up. Yeah.
And where's the power fail protection for that DRAM? Do I need a UPS behind this?
No, you do not need a UPS or anything. It's all built into the system.
So there's sufficient capacitance in the system to dump all that DRAM?
Right. So the DRAM at the VIM level is basically, upon a power event, is flushed into the flash, and it's pretty much protected in that manner, without any higher level need for enormous batteries or anything of that nature. Yeah. Again, another benefit of having our own custom designed rather than off-the-shelf storage components.
So, and this is a good point, that you raised again here. No UPS required and no dependency on any external SSDs. We don't have any SSDs anywhere.
So, just focusing here a little bit on the data path, because I know there was a very busy diagram up here. You can see here we have basically redundant paths to the VCMs. We have basically it's a PCI switched environment within the box that connects our gateways for the storage compute, HBAs and NICs, and then down into the VCMs again, and replication ports that we can talk about some of our features as we go on. No single point of failure, and as I'll talk about in a little bit, these parallel paths are the key to our performance. The other thing we get from the design is we have an independent control plane. So in that, nowhere in the data path are you intermixing the control path messages. So when you're having the hardware-based RAID in the communication across PCI, we have separate monitoring bus through Ethernet to do logging and configuration, upgrades and all that, separate from the actual data path. And then finally, we have what we've been calling our flash fabric here. This is the intercommunication between the VIMs, where the actual data is stored, and the VRAID hardware controllers, the VCMs. So what we have here is actually a very custom designed Violin fabric, leverages what we call our channel technology that has been around. It predates actually the 6000, dates back to some of the boxes you might see in our previous generations. And that is, again, a key, and I'll go into a little bit of detail of how we get both the resiliency and again the performance.
So it's
out
not
of it.
SAS, it's not SATA, it's your own internal
Yeah.
device control.
Exactly, it's a data. It's our own data control, data and control at this point protocol.
Which is outdated latencies.
So and it's been proven that's been, as I said, it's been used back into our previous 3000 series, and I believe it dates back even before then. So it's a technology that was baked and designed well before some of the competing technologies that are out there now, and we continue to drive it and ride the performance curve with increasing bandwidth and performance.
What are the SP
So what-
blocks there?
Pardon me?
What are the SP blocks there?
SP spares. Sorry.
Oh,
So
okay.
in the next diagram, we'll show a little bit detail, but 60 active VIMs, 4 spares is the max configuration of our box.
Yeah, if I could elaborate. So again, you picked up something very interesting when you picked up the interconnect. So when this box was rolled out, several years ago, there weren't fast enough interconnect to connect the PCM, the V-rate controller we have and the VIM we have. Even today, as we keep looking into the ecosystem, because we want to also leverage whatever is there in the ecosystem available, but we still haven't found the fabric which gives us the price, the same level of bandwidth and density that we have gotten over here, and the same level of features. So it's very interesting what the founders, and I'll not take any credit, I wasn't the founders. It's incredible what the founders have put together, which has carried us through all this while. And as we look into the ecosystem to incorporate some of the things, we still don't have it. And there is some deeper section that is coming out that Chris will talk about to show you what those things are.
And how much throughput can you put through the back end there?
So there is a performance pipeline coming up, but basically in this ecosystem, so we claim 1 million IOPS, but this system is capable of 2.5 million IOPS in 3U box.
And bandwidth-wise?
So you can do the 2.4K, so roughly 10 to 12 gigabytes per second. Yeah.
And this is PCA Gen 2, right?
At this level, yeah, this is currently PCI Gen 2 in with thoughts of as we drive forward.
Obviously, a thing for us for some time. Go to Gen 3 is going to happen for some
Steve,
time.
they can't hear you.
But,
Steve, start over. Steve, they can't hear you.
Sorry. Yeah, you talked about the Gen 2. So we're going to Gen 3 right now, but we didn't need to go to Gen 3 yet until now because we're getting the same speeds. So when you walk through the system side, when you go from the VCMs to from the VIMs to our VCMs to our compute and then out to the HBA, our calculations were actually keeping that at PCI 2 at the super speeds we needed to. Now we've actually hit that limit, and you'll see Gen 3 out of here very soon, and then on to the next one.
So, taking a deeper dive into the flash fabric here, this is just that bottom part of the graph blown up. What we see.
Somebody's been using their PC board tracing software to draw that slide.
Inkscape. I'll share a little story where we got from our founder and CTO, who claimed that one of the original board designs he actually did in PowerPoint. So
That's that.
the guy is brilliant and I guess a masochist.
Yeah, I'd agree with that.
So what we have here are 60 VIMs, these small little boxes, each connected to 4 VCMs, and we also have the spares here. And what you'll note is that each one of these VIMs is actually what we would term triple ported. It has 3 I/O ports on each VIM, and what that gets us is a rather elaborate but very resilient tree structure here, in that any VIM can be contacted by any of the VCMs in order to provide complete redundancy in access and communication to that VIM, regardless of other VIMs being down or VCMs being down. As part of our V-RAID system, what we do is we break everything up into separate RAID groups. What you'll see here is actually within a fully populated system, each VCM ends up having 3 RAID groups. So I've tried to color code within each VCM. These different colored VIMs are indicative of the different RAID groups that you'll see attached to that VCM. So 3 shades of blue here for those 3 RAID groups, 3 shades of red, green, purple. I'm not colorblind, I guess. So that gives you some indication of just how the RAID's set up. One question that might come up is, well, why is it so apparently scattered as this? One reason is when we talk about the channel, which is this interconnect between the VCM and the VIMs, we've laid these out both for resiliency, but to give a common performance level across all the RAID groups. You can imagine if all of one RAID group was closest to the VCM, that would get a little bit better performance than the ones that were a couple hops away. So by doing a staggering method like this, it gives a consistency and a high performance across everything. And
Is it 4 plus 1 RAID?
Yes, it is. It is at this point 4 plus 1 RAID, and I'm focusing on more the fabric and the communication aspect here. Chris is going to talk a little bit more about the RAID controllers and all that, so we can do a deeper dive into that. But they are very closely tied together in the way this is all done.
Why have you chosen to organize the RAID groups under a single VCM and not spread the RAID group on all VCMs?
It has to do with the way at the hardware base, basically the whole ecosystem of when we do parallel writes and parallel IOs of any sort, it's divvying up a 4K write or IO to a given VCM, and then that is responsible for handling all the individual VIMs beneath it within the RAID group. So it gives, makes it more of a stateless and doesn't require any of the VCMs to have any, at the data path, have any communication with each other. It makes it purely parallel.
Each VCM acts like a RAID controller rather than having the whole thing act like a shared nothing cluster.
Right, exactly.
And I think I'll make one of the comments here. So this was introduced as industry's first flash optimized 4-way HA RAID controller, and it still continues to be that ways. So all those VCMs that you see communicate with each other, right? In the clustered fashion because the statelessness, they can take the ownership without having to worry about what needs to be flushed. And it's done at the hardware level. And so only 4-way, HA controller, hardware driven, that exists in the industry at this point.
There's some people at HP who argue that.
So we have to see the product then. We haven't seen the 4-way HA controller which can manage all the device together, the pool of device that they had, the way we have put together.
So as we move on, talk a little bit about what happens and how we leverage this triple port design and tree architecture to handle failures. What you can see here is I've actually had one of these VCMs fail. And these bold lines here now indicate how using the alternate path between these VIMs, this VCM here, the blue VCM, has now taken over ownership of all the red groups as well. And it is able to, this is, the tree dynamically reconfigures when it discovers an issue with a VCM being down. And so now, basically, ownership of these RAID groups are now owned by the VCM, and at the higher levels, it actually doesn't really have to do much at the higher level. It's all handled at the hardware RAID level and beneath it.
What kind of a performance impact would that have? Anything?
It does have a minimal, well, not insignificant performance impact, because one of the reasons we have the 4 VCMs is parallelism for performance and all that. So losing one of these main engines does have an impact on performance. I don't have the numbers myself to say how much
roughly 10%
it goes down, but it certainly is beneficial, and it's an automatic hot failover and all that. So and interesting enough, this actually will work, and you can take down 3 out of 4 of the VCMs and still have the system completely have complete access to all the data on the system. And this failover mechanism actually, Pat will talk to it in a little bit, is also actually the key to how we do part of our NDU, our non-disruptive upgrade of the system. We actually can fail over all the data access paths, do upgrade, and move on to the next component. The tree fabric also gives us the ability to handle Vim failures. So in a similar manner, if you see here this X'd out box here, if that Vim has been removed or has a hardware failure or some sort, it will the fabric will reconfigure and use one of the spares here as an alternate for that missing Vim. At the next higher level, the V-RAID controller will handle, rebuilding RAID onto this new spare, but it's all done without any direct hands-on intervention by administrator or so.
How long would a rebuild generally take, and what's going to happen with performance there during the process? Just curious.
Chris, can you talk to that? I'm not as familiar with the timing on the RAID rebuilds.
Yeah, definitely. So there are two cases where we go for the rebuild. One, when there is a soft Vim failures, and those are more common. And the soft Vim failure is when some firmware went wrong or something, but we have a way to determine. So we reboot it. So when we reboot it in place, there's only delta thing that we have to build. Whatever the delta write was, that is in a couple of minutes. That goes very fast. Then there is the brick where the Vim is unusable, complete unusable, and assuming that we have not been able to predict. So we have this mechanism in place where we are constantly looking at the blocks, getting bad and moving the blocks off to the healthy Vims and all those things. But let's say assume that all those things have failed. First of all, it shouldn't fail, but let's say it has failed and the Vim has basically gone brick. I think we have had so many. I think in the company history, we have heard 3 or 4 of the Vims that have completely been dead. In that case, it's dependent on the size of the Vim that we are using, whether it is 512 gig or 1 terabyte or 2 terabyte that is there. Depending on that, and since the given bandwidth we have, it can take all the way up from 30 minutes to 2 hours, something. Yeah, a couple of hours.
Can take
a complete full build if you're talking
3-4 hours.
Yeah.
To review. Only on the entire component failure.
Right.
Yeah. Normally we actively scrubbing and detect the page failure and doing the rebuild upfront to prevent the full component level rebuild. So
and again, this is an excellent question because that goes right back to why did we choose to design ourselves? Because now we have bidirectional communication between the Vim and the VCM. So we are actively communicating. We are looking at the bad blocks, and before the Vim can actually get dead, we are moving the blocks to a different member in the RAID group, and we can make a decision to include the spares and all those things, so that we can avoid the situation where the SSD just bails out on us. And avoid. So exactly, you're right. So we want to avoid that RAID rebuild altogether, and that's where a lot of IP has gone in. That avoid if you can the complete RAID rebuild.
So with the 4 spares, we can actually handle from a fabric point of view 4 missing Vims. I show here three Vims actually being down with still an extra spare ready in case, and God forbid, something else happened. But the way that the spares are located, they can be shared. They're basically, any VCM can grab one of the spares as needed and be able to handle more resiliency.
There's a question that came in on Twitter, if you don't mind.
Certainly.
If any cell on any NAND chip inside the Vim goes bad, does that mean the whole Vim is bad?
Certainly not. So I think that will be something that, as we do a further deep dive into the VCMs and then especially the Vims, I think Chris will be able to talk far more into that detail. But the whole the way we built the system is there's redundancy at the system level. But if we were to pull apart the Vim at the same way, there's a large amount of redundancy in CRCs and various things to ensure that one block or one flash chip doesn't cause the entire Vim to go down. And so one takeaway from this is the fabric by itself handles communication and access issues with as many as 3 VCMs and 4 Vims being down. But when we factor on V-RAID on top of that and the way the RAID works, we can tolerate as many as 16 Vim failures in a box without any data loss. Any questions? And last point I want to make here is just to talk a little bit about how the parallelism in our system actually drives not just the redundancy we've already talked about, but also the performance. And what this has done is just through having the multiple data paths basically throughout the entire box.
Jim, can you go back to that prior slide just for
Certainly.
a second? How can you handle 16 VIM failures?
It's from having the 4 hardware failures, and then it's within a particular RAID group. If there's an additional failure of VIM, the data is still accessible through the other members of that RAID group. So these 4, so if you had the first 4 VIM
No problem with
failures,
the first 4. I understand that.
all the RAID, everything is still fully populated with RAID groups. That's all fine. And from that point on, you start with getting into.
So when you get another 4 failures, you've lost effectively parity. I mean, to some extent.
Okay.
Yeah, you get.
That's 8. I understand 8.
But it's split across. You can be split across any of these 64. So we're when the spares take into account.
16 failures is assuming there's enough time in between them to rebuild.
No, so okay, I'll handle 12 RAID groups, 1 spares each, that's 12, 4 spares, 16.
Yeah.
12 plus 4, 16.
Up to 1. It's the same as the discussion we had yesterday, up to 1 failure per group.
Yeah, so and this is where this goes back to the conversation that we have put in a lot of IP with building in this, that we don't have to go into this RAID rebuild and all those things. You're always ready to take over as soon as you determine a VIM to be lost. So that's where we claim 12 plus 4, 16. So that's how 16 comes in.
It's a distinction between
hardware
level and operating in a degraded RAID mode.
As an engineer, I will argue that if you're going to tell me 16, I'm going to say that has to be any 16, not the right 16.
Right.
Yeah, I grant you that. So let's say a catastrophe, catastrophic events happen, and all 16 within. So all the VIMs in one RAID group
through 15 all die.
Yeah,
that's
right.
being able to survive 16 failures,
Right.
and you don't do that.
No. So in that case, when your entire 4 or 5 VIMs go down, then we haven't architected the platform right.
Right.
That all the 4 in the RAID sets are going down.
I'm not arguing that this is a failure of design. I'm arguing this is an overstatement. That if you tell me, it's like arguing that if I'm running RAID 10, I can afford 2 drive failures as long as it's not the 2 drives that are mirroring the same data. Well, the as long as is not a valid argument.
Okay, so I'm going to take a little bit
I can
here.
survive 16.
Yes.
I'm saying I can survive any arbitrary. That in order for that to be true to me, you have to be able to survive any arbitrary 16 all at once.
Howard, he says this slide says as many as. I mean, that's a qualifier.
As many as 16 VIMs.
So, yeah, if you lose 16 of the wrong ones, which first of all, the odds are freaking astronomical.
No, that I'm not arguing.
That is exactly what I was going to say. I mean,
I'm not arguing we're not more likely to get hit by an asteroid and killed in this room before that happens. There's just commentary on the statement, not on the technology.
We already had that analogy.
Okay. It's one of my favorite analogies.
So. Just talking about the parallelism here, just want to walk through real quickly the data paths we have. We have multiple HBAs are connected to the SAN via the different protocols we mentioned. The inbound requests, actually, if we get larger than 4K requests, we pass them down into flash optimized 4K requests from the MGs down through the switches to the VCMs. At this point, as we alluded to earlier, the VCM actually then splits into a number of 1K requests at the actual VIM level, as it said here. And then what this basically means, when you take the 12 RAID groups across the whole thing, 5 VIMs within each RAID group, we're actually doing at any given time 60 parallel IOs, going at any given time. We look at what this means as far as aggregate at each one of these pipeline levels. When we talk about 4K IOPS, this is what we see as being capable for the various protocols and the pipelines that we have. And this speaks a little bit to Steve's point earlier, well, why haven't we moved on to PCI Gen 3? When the actual transports in the pipelines we have been, been suitable for what we are actually doing at a system level. And then when we talk about what this means at the system level, hardware capable of, in this 3U box, of doing 2 million IOPS at peak. And what we look at when we talk about the back end, which would be talking about from the MG driver down through the VIMs. Currently, we can do 760K IOPS at 100% right, sustained. This isn't a peak number. This isn't doing fancy reads and buffer caching. This is straight on writes. And the system, the architecture we have now is capable of getting up to 1.5 million at that same level.
When you say sustained IOPS, you're talking about random, not sequential, and it doesn't really matter.
And as we get into the past the right cliff that some people have with garbage collection and all that, this is, you've been using the system straight for days, weeks, months. This is the we promised this is what you get, not the all right, well, it came out of the box and wow, it looks great, and then throw it into production and 3 months later, what happened to all that performance I thought I bought? So that's one of the driving points throughout the entire design is consistency, high performance, but consistent high performance.